This video is a deep dive on a problem I first saw on Twitter about coin flips. It was really popular on Twitter. It got over 50,000 votes. I call this problem Alice heads heads versus Bob heads tails. Here's how it works. First, we're going to flip a coin 100 times. So we have a sequence of heads and tails of length 100. Every time there's a heads heads, so 2 heads in a row, Alice gets a point. And every time there's a heads tails, a heads followed by a tails, Bob gets a point. So for example, the sequence tails, heads, 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 tails, Alice gets 2 points and Bob gets 1 point. Alice gets 2 because there's the first heads heads and the second heads, but Bob only gets 1 from the last heads tails. And the question is, in this sequence of 100 flips, at the end of flipping 100 coins, who is more likely to have more points, Alice or Bob? And on Twitter, of course, most people thought it was equally likely. That is wrong. That's the thing that makes this exciting. One of these two players is slightly more likely than the other to win. So one of them has a 48.58% chance to win, and the other has a 45.76% chance to win, with ties making up the rest of the 100% pie. And a lot of people on Twitter had some discussion. People noticed almost right away that Alice is more spread out. So because Alice is going for heads heads, and she can get like a long sequence of heads in a row, Alice can score a lot of points. Alice's distribution is quite spread out here. That's this distribution in blue. And Bob, on the other hand, is more narrow. So the variance of Bob is much less than the variance of Alice. And people were arguing about this. What does that mean? Who is more likely to win based on this? The thing is, they both have the exact same mean. So on every 2 coin flips, there's a 25% chance that either of them will score. And by the linearity of expectation, their average over 100 flips, because there's 99 chances, 99 pairs of coins next to each other, their average is going to be 99/4 for both of them. So they have the exact same average. So this spreading out, what does that mean? Who's more likely to win? And a lot of people were arguing, oh, that means Alice is more likely to win, or that means Bob is more likely to win. But this is the thing about this problem, is that you can never actually figure out who is more likely to win just based on looking at their scores individually, like we have here. And the reason is, this was a very clever argument I also saw on Twitter. If you give them extra points, you will see that it's impossible. And if you give Alice an extra point every time a tails tails comes up, and if you give Bob an extra point every time a tails tails come up, what do their distributions look like? They look like this. So here is the distribution of heads heads plus tails tails. So if you give them a point every time there was a heads heads or a tails tails, same with Bob, every time there's a heads tails or a tails tails, give them a point, then they have the exact same distribution. Now, of course, if you give them both extra points every time a tails tails happens, who is going to win the game doesn't change at all. So it's the exact same probabilities as before, but now their distributions are completely indistinguishable. They're exactly the same. And so the secret in this problem is that it depends really heavily on how Alice and Bob interact, right? How do heads tails affect heads heads happening, and vice versa? So you can't just look at their distributions individually. These are called the marginal distributions. You have to look at the whole thing together. They're joint distributions. Somehow, how are they going together? So if you've never thought about it before, I highly encourage you, take a guess who you think is going to win. Is it going to be Alice or is it going to be Bob? In the rest of the video, I'll tell you the answer and show you some nice intuition on why. So here it is. I'm going to spoil the answer in 3, 2, 1. The correct answer is Bob. Bob is more likely to win. So Alice has a 45.76% chance to win, and Bob has a 48.58% chance to win. And in the rest of the video, I'm going to give you some nice intuition that I came up with that explains why Bob is more likely to win. And it involves this dog running around on the soccer field. So there's going to be an analogy with Alice and Bob playing soccer, and this dog running on the soccer field is going to explain why Bob is more likely to win. I'm also going to show you how I calculated these exact probabilities. So there's a very nice method using Markov chains and value functions, which is a really great method in all of probability theory. And you can calculate these things for any length of game. So no matter how long the game is, you can figure out the chance that Bob wins, that's up here. The chance that Alice wins, that's up here. You can see that Bob is always a little bit more likely to win. The chance of a tie is going down to 0. And you can use this, to prove that Bob is always higher than Alice. So even without calculating, you can turn it into a proof that Bob is always higher than Alice. Not only that, when I was doing this video, I realized something very interesting, which is that if you plot Bob's advantage, so we know Bob is higher than Alice, but if you actually take the difference and plot that as a number, and you'll notice something interesting, which is that it's almost exactly half of the tie probability. And in fact, not only is it almost exactly half, there's a nice formula for both. So here's the nice formula. The probability of a tie is 1 over square root of pi t, and the probability of Bob's advantage, probability Bob wins minus probability Alice wins, is 1 over 2 square root of pi t. And what this means is, for our original problem, the probability Bob wins minus the probability that Alice wins, it's 2.82%, and that's approximately 1 over 2 square root of 100 pi. And that error is extremely tiny, less than 0.002%. And I found a really nice proof of why this is. So that'll also be towards the end of the video, explaining these asymptotics and where they come from. And this factor of square root of pi is actually not unexpected. It comes from the central limit theorem. So first up, let me do the intuition, this nice soccer analogy. So what does a dog running onto the field have to do with Alice and Bob? And what I'm going to do is I'm going to describe a situation that we're more familiar with, a soccer game with a dog running onto a field, and then I'm going to explain why that is similar to the Alice and Bob coin flip game. Okay, here we go. Imagine Alice and Bob are playing a soccer game. Most soccer games are 90 minutes long. We're going to make this one 100 minutes long so it matches the number of coin flips in our problem. And we're going to very carefully enforce that there's no extra time. So in a real soccer game, sometimes they add time at the end. For us, 100 minutes exactly, and then it's over. In every individual minute, we're going to say Alice and Bob are equally likely to score. So in minute 47, who's going to score? Could be Alice, could be Bob, equally likely. Okay, here is the special weird rule that gives Bob the advantage. And I'm going to explain why this weird rule is like the situation in the coin flip game. And hopefully that'll give us some intuition of what is going on in the coin flip game. The special weird rule is that whenever Bob scores, a dog runs onto the field. And the thing is, this dog is going to distract everybody, and nobody can score until the dog is off the field. So the dog is sort of going to run out of the field and waste some time. But the countdown clock of the 100-minute game is going to keep ticking down. So this dog is effectively shortening the length of the game. They are eating up time away from the clock where nobody can score, and they do that every time Bob scores. Now I claim it is intuitive that this dog means that even though Alice and Bob are both equally likely to score, Bob will have an advantage in this game. And the reason is the dog only happens when Bob scores. When Bob scores, they are more likely to be winning the game. So you can imagine if the dog only ever ran onto the field when Bob was winning the game, that would be a huge advantage for Bob. In fact, some soccer players do this on purpose, right? They waste time when they're winning. When their team is winning, they try to waste time with the ball, and that is what the dog would be doing. This dog is not as good as that. They don't only waste time when Bob is winning. Sometimes they waste time when Bob is losing and would like to not waste time, but they waste time whenever Bob scores. And when Bob scores, they're more likely to be winning the game. So it's sort of like a very small advantage given by wasting time that is more likely to be time when you are winning the game. And when you're winning the game, you want to waste as much time as possible so that the other team doesn't have a chance to catch up. Okay, that's the soccer analogy with the dog. Hopefully this makes sense to you, intuitive sense. Now let's see in what way this is similar to our coin flip game. So in our coin flip game, of course, it's not a soccer game, it's a coin flip game. It's a game with 100 coin flips. So think of one coin flip is like 1 minute of the game. It's going to be exactly 100 coin flips. There's no extra time. And on every flip, both Alice and Bob, I claim, are equally likely to score. And the reason is, if a heads was the previous thing that flipped, so if a heads was the last coin flip that came up, then Alice will score if the next coin flip is a heads, and Bob will score if the next coin flip is a tails. So given that the last coin flip is a heads, they're both 50-50 to score. Alice scores on heads, Bob scores on tails, but they're both equally likely 50%. Okay, here is the special weird rule. I put it in quotes here because it's not a special weird rule. It's an emergent rule from the fact that Bob is going for heads, tails. In the soccer game, I just made up this rule, right? This dog. But in the coin flip game, it's happening automatically by the very nature of heads, tails. And what is happening here is that whenever Bob scores, no one can score for a few turns after that. Why is this true? The reason is, when Bob scores, a tails was flipped. And after a tails is flipped, neither of them can score for a while. So a tails is sort of like the dog being on the field. Every time a tails comes up, Bob has scored his goal after a heads, tails. And then there's some sequence of tails, maybe only one tails, but maybe like 2 or 3 tails, maybe even more. And while this is happening, neither Alice nor Bob can score. They cannot score until the next heads comes up. So this tails being flipped is a little bit like the dog running onto the field. And there's some amount of time that is wasted every time Bob scores. And it's just like this situation over here in the soccer game. Every time Bob scores, time gets wasted, and that gives Bob a little bit of an advantage because when they score, they are more likely to be winning. And when you're winning, you would like to waste as much time as possible. That's what this time wasting essentially does. Okay, this is the intuition that I came up with. How can we turn this into a proof? So I'm going to turn this into a mathematical proof where you really see this idea that a tails is wasting time. That is crucial in the proof and is exactly there. And so what I'm going to do is I'm going to first show you how I got the computer to calculate these probabilities. So the probability of Alice winning and of Bob winning. So it's a nice trick using Markov chains and value functions. And that trick will also let us see a theoretical proof why Bob always has an advantage. So it'll let us calculate this Bob's advantage directly, and from which we can see that Bob really always does have an advantage. So what is the trick? The trick is, instead of thinking of coin flips, where there's, in a length 100 game, there's 2 to the 100 possible things that could happen with the coin flips, instead, just condense the information you need into just one number and just keep track of that number as you go. And in this Alice-Bob problem, the number that you need is 2 things. You need the score difference, Alice's score minus Bob's score, and you need the outcome of the previous coin flip. So I call these things xt, which is a random process evolving in time. At time 0, that's the beginning of the game, Alice's score is 0 and Bob's score is 0. And then over time, it evolves, it goes up and down, because when Alice scores, it goes up by 1. When Bob scores, it goes down by 1. And at the end of the game, we want to know if it's positive or negative. It would be great if we could only look at xt. That would be like a random walk. That would be really nice, well studied classically. But in this game, you also need the extra piece of information, ct, which is what was the coin at time t. And the reason you need that is because Alice and Bob can both score only if the previous coin flip was a heads. If the previous coin flip was a tails, then Alice and Bob won't score. And it is this delay when ct equals tails that is exactly my analogy with the dog. I kind of think of when ct equals tails, that's like the dog is on the field wasting time. When ct equals heads, the game is on, and xt will evolve just like a regular random walk. So let's see what this looks like. This is called a Markov chain. Here is a little picture of it. Before I tell you what the picture is, let me write down the rules I just said out loud. So if ct equals heads, then on the next coin flip, xt can either go up by 1 or down by 1. So xt plus 1 will either be xt plus 1, or it'll be xt minus 1. And these are both 50% chance. And you can see that in my little diagram. What I have shown is I've drawn a little state here for every x value. I've drawn x comma heads. That means xt equals 0 and ct is heads. And you see it's connected either half the time you go to the right and it goes up by 1 and a heads is showing, or you go down over here and you lose 1, you go down by 1 and a tails is showing. So you can either go down or right, and they're both equally likely in this diagram. And this happens for every single x value. So no matter what x is, you always have these connections. On the other hand, if ct equals tails, that means a tails is showing, then xt plus 1 is just equal to xt, it doesn't change. And this is shown in my little diagram of these little loops, right? If you flip a tails, you're still where you are. If you flip a heads, you move up to the other thing. But in either case, xt, this column here, does not change. So this little diagram kind of shows you how the states are connected, the states here being pairs of xt and ct. And this shows you how they're connected, right? Half the time you go up by 1 and you either change heads or tails depending on if you went up or down. And half the time, if you're in a tails, you either stay where you are or you switch to the heads state. And I kind of think of this whole bottom row here where a tails is showing as the situation where the dog is on the field wasting time, and the real game is happening over here where either player can score. Okay, so this is the Markov chain I'm using for this thing. Markov chain means if you know the state, you know what happens. I just told you exactly how things evolve, so we know it's a Markov chain. Okay, what else do we need? We need to convert this into calculating probabilities for Alice and Bob winning. In fact, I'm going to calculate it all together at once. I'm going to calculate the difference between Alice winning and Bob winning by using this victory point function. So I have these things called VPs, victory points, and I'm going to say if Alice wins, there's a +1 victory point assigned to the situation, and if Bob wins, it's a -1 victory point. So this is like the number of victory points that Alice gets. And a tie will be 0 victory points. And what I'm going to do is I'm going to calculate the expected value of this victory point function applied to x100. So x0 is the beginning of the game when neither of them has scored. x100 is the end of the game. And by applying this victory point function, because it's either 1 or 0 or -1, its expected value is exactly +1 times the probability that Alice wins, -1 times the probability that Bob wins. Right? So by taking the expected value of something that is either 1 in one situation and -1 in the other situation, depending on if the goal difference is positive or negative, it's going to tell us the difference between the probability that Alice wins and the probability that Bob wins. That is exactly what we want. This is exactly the thing we want to calculate. Okay, so now we have our Markov chain, xt, ct. We have the thing we want to calculate as some expected value involving the Markov chain. How are we going to calculate it? We're going to use something called value functions. So what is a value function? A value function is just doing this expected value given some intermediate information. So specifically, I'm going to define vt of xc if you're given some intermediate information about the game at time t, you know the score difference x and you know the current coin flip c, together you can calculate the conditional expectation of the thing we want. And this is just like the situation where you are watching the game, you're watching Alice and Bob play the game, and you look at your watch, it's time t, the game ends at time 100, and you see on the scoreboard that the goal difference is x and that the current coin flip is c. And you say, given this current situation, what is the difference between Alice's chance to win and Bob's chance to win? Calculate the expected value given what we know in this intermediate situation. I always think of this when I go to like a baseball game or something. I'm always imagining this value function in my head. I'm watching the game, you know, it's like the fourth inning, there's somebody on second base, but they're down by 2 goals. And I'm saying, what is the chance they're gonna come back and win from this situation? That's exactly calculating a value function given the information you have now. And the nice thing about these value functions, you might say, okay, well, does this actually make the problem easier? Like, you wanted to calculate one thing, now you've done this like weird conditional stuff. How does that help you? And the reason is, these conditional things can depend on each other. So we can find a recursion relation for these value functions, how they depend on themselves, and we can use that to solve and see what's going on. And in particular, these satisfy a really nice recursion relation. The recursion relationship is written here. I call them the update rules. And there's 2 kinds of things that we know. One thing is we know V100. V100 is at time 100 if you have the knowledge of what's going on, right? So if you put in t equals 100, then you know xt exactly. So this is a little bit like at the end of the game after the referee blows their whistle and you ask, what is the chance of Alice winning minus the chance of Bob wins? Well, you know exactly what it is. You're done the game, you know what the score is, and so you know exactly what V100 is. That's at the end of the game. And then this is the cool thing, is that you can always figure out what happens 1 minute earlier using what happened 1 minute later. So you can figure out Vt minus 1 using Vt. And in fact, it is literally the update rule that I just drew over here, right? That was an update rule for probabilities. That turns into an update rule for the expected values. And I've drawn them over here. There's 2 kind of update rules. One is updating what happens if heads is the current thing. So imagine we're at a situation where we want to know what is the chance of Alice winning minus the chance of Bob winning when a heads is showing. Well, half the time, another heads will come up and the score difference will go up by 1, +1. And half the time, a tails will come up and the score difference will go down by 1. And that's exactly these 2 paths over here and over here that we did before, right? So half the time we go up by 1, half the time we go down by 1. That is exactly encoded in this equation for Vt minus 1, heads. Similarly, if we are currently showing a tails, then half the time it'll be a tails again, and half the time it'll be a heads again. But either way, the goal difference x does not change. And that is exactly encoding these 2 rules, that you stay where you are, the x value doesn't change, even though the ct value changes. So basically, the rules of this Markov chain of xt, ct get encoded into update rules for the value function. And this is something you can always do. If you know the Markov chain, you can figure out how the value function is evolving. This is a really commonly used technique. For example, if v is the value function for stocks, then you get these equations are exactly what people call the Black-Scholes equation, and they're partial differential equations. For us, they're discrete time updates because we're playing a discrete time game, but otherwise it's exactly the same. So we have these update rules. You can put these in the computer and get the exact answer, and that is what I did. So here is what it looks like when you ask the computer, please solve these equations, which you can do with a big for loop, first starting at time 100 and working your way back to time 0. Okay, so here is a plot of the solutions that the computer found by using these equations that solve for Vt for every value of t between 0 and 100, and here are the plots. So first, most important thing maybe to keep an eye on is the value of t is over here in the corner in the legend. Here is t equals 100, which is the end of the game. On the x-axis over here is the score difference, and this is in units of goals, and +1 means Alice is winning, so +1, +2, or +3 means Alice is up by 1 or 2 or 3 goals, and -1, -2, or -3 means Alice is losing by 1 or 2 or 3 goals, so Bob is winning. On the y-axis is the expected number of victory points, going between -1 and +1. +1 means Alice wins for sure, and -1 means Bob wins for sure. And again, this expected value is really like the chance of Alice winning minus the chance of Bob winning. That's another way to think about it. But either way, it's the scale going from -1 to +1. And at t equals 100, like we have here in this very first plot, it is a very boring looking function. It's exactly the victory point function VP. And that is because t equals 100 is the end of the game. So if you are given the goal difference at the end of the game, what is the chance of Alice winning and the chance of Bob winning? Well, there's no randomness at all. Like, the game is over, either Alice won or Bob won. So if Alice is winning by +1, +2, or +3, then you get a +1 victory point. And if Bob is winning -1, -2, or -3, then you get -1 victory point. There's no randomness at all. And this is a very boring situation, but this is sort of like the initial condition, and then we're later going to iterate to solve from there. And this is the first rule I said over here. The initial condition, v100, is exactly the value function, the victory point function, vp of x. So that's t equals 100. What happens at t equals 99? At t equals 99, it starts to get a little more interesting. You can calculate exactly what's going on, and that's what the computer did using this update rule. But first, let me do this one by hand and calculate this value by hand. So you'll see that when a heads is showing, let's calculate this value. So here, this is the situation where Alice is up by 1 goal and a heads is showing. So imagine you're at the stadium, there's 1 minute left in the game, it's like a close game, Alice is winning by 1 point, and there's 1 coin flip to go. If the last coin flip was a heads, that's what's shown over here. If a heads is showing and the last coin flip was a heads, then on the next coin flip, either Alice will score again or Bob will score. So we have a 50% chance a heads comes up and Alice scores, and a 50% chance a tails comes up and then Bob scores, because there was a heads before, a tails, then heads, tails. If Alice scores again, then Alice will be at +2 and she will win. So that will happen half the time. So 50% chance Alice wins, and when Alice wins, you get 1 victory point. But there's also a 50% chance that Bob wins, and you get 0 victory points. And that's because if Bob scores, it will be an exact tie, and in an exact tie, there is 0 victory points assigned. And that is why this thing is 0.5. If you do 50% times 1 victory point plus 50% times 0 victory points, you get 0.5 victory points. And that is exactly what is being shown over here. So these things, you can calculate them exactly by looking at all the possible futures. When there's only 1 coin flip to go, it's pretty easy to do, and it makes intuitive sense. I will point out that if a tails is showing, then Alice is going to win for sure. And that's because if a tails is showing, then there is no way for anybody to score on the last coin flip. So if a tails is showing, it's like basically game over. And this is a kind of a theme you're going to see. It matches the intuition with the dog, is that the tails are kind of like shorter games and the heads are longer games. So that's how you can calculate it directly and what it means. But now let's also calculate it using this update rule. And that's exactly what the computer was programmed to do. Here's how the computer did it. So the computer says, I want to calculate what's happening at x equals 1 and at t equals 99. And wherein the coin flip is heads. It's going to use this update rule right over here. And what it's going to do is it's going to look back in time by 1, and it's going to average the value functions from the previous time. So it looks at this previous time that we know, we've already calculated it, and it says, I'm going to add 1 to it and look at the heads situation. So it's going to say, look at v100 of +2 comma heads. So half the time a heads comes up and we go +1. So we take 1, we add 1, we get +2. That's this rule over here, adding 1. And on the other hand, half the time it's going to go down by 1, and it's going to be a tails. That's this rule over here. So it's going to be v of 100 of 0 comma tails. Okay. And it's going to take those two values. On one situation is a dead tie, 0, and the other situation is a +1, and it's going to average them. And averaging, of course, is the same visually as taking the midpoint. So we're going to have kind of the midpoint between these two things right here. The midpoint between 1 and 0 is exactly 50%, and that's exactly our heads value from before. So it makes perfect sense the way it came out by using this update rule. And we're going to see visually that this update rule of taking the midpoint is going to sort of explain why Bob has an advantage in the game. Okay, so now let's look at t equals 98, and it starts to look like this. And so at t equals 98, you can already see here in the middle that Bob has an advantage, right? Because this is less than 0 means Bob advantage, right? So when the game is currently a tie, even though the game is currently a tie, if a heads is showing and there's only 2 rounds left, then Bob is going to have an advantage. And we see that in our thing because this is less than 0, and Bob is the negative victory points, and Alice is the positive victory points. So being below 0 means Bob has an advantage. Why is this less than 0? Well, there's only 2 coin flips left, so you could go through all 4 possible things, what could happen on the next 2 coin flips, and figure out when does Bob win, when does Alice win. Or you could use the update rule. Let's use the update rule, just like the computer does. So we go back in time by 1, and we average these 2 things. So what do we average? we average this one over here, right? This is v of 99 of +1 comma heads. And we average it with this one down here of v of 99 of -1 comma tails. And we average those two things. That's the midpoint. We take the midpoint of these two things. It's somewhere like this. Okay, and indeed, the computer did it exactly right, and it averaged those two things to get the value, which is slightly below 0. Why is it slightly below 0? Well, the reason it's slightly below 0 is because on this side over here, where Bob has the advantage, v tails is lower, right? So every time Bob has the advantage, when the goal difference is negative, then v tails is lower. And every time over here, where Alice has the advantage, v heads is lower. Okay, and this totally corresponds to the intuition with the dog, right? When the dog is on the field, if Bob is winning, then that's great for Bob, right? Tails showing means there's less time effectively left in the game, and so winning the game is better for Bob when Bob is winning. On the other hand, here, it's better for Bob if there's a heads showing, right? If Alice is currently winning, then it's better for Bob if a heads is showing. That's because it's a longer game and Bob has more time to recover. So a heads is better for Bob when Alice is winning, and a tails is better for Bob when Bob is winning. It makes perfect sense, sort of intuitively. And now you see, when you do this kind of averaging, you are always averaging. If it's a tie game, you're always doing the average in a way that is favorable for Bob, right? You take v heads at +1, you take v tails at -1, you're always doing the average of these two numbers. You're doing the average of the two numbers that are better for Bob in both situations, right? If a heads comes up, then Alice is winning, but it's the better for Bob situation. If a tails comes up, then Bob is winning, and it's the better for Bob situation. So because v tails is lower over here and v heads is lower over there, then you always get this thing that it's always better for Bob. And that is kind of the intuitive answer I came up with for why Bob always has an advantage. Okay, and you can kind of explore what the computer found. So here are the solutions at t equals 97 with 3 rounds remaining. By the way, a lot of people on Twitter, they did this one explicitly, right? So they said, starting with, what if there were only 3 coin flips, and they calculated this value exactly. I think it's a -1/8 here. This is the advantage for Bob. But you can see that it always does what I said, which is that v tails is always lower. So kind of to draw an extreme example, it kind of looks like this for v heads, and then v tails is more extreme like that, and it always is working in a way that's favorable for Bob. Okay, and here's what it looks like at t equals 96, same idea, t equals 95, same idea, but less extreme, right? As time goes on, the difference between a tails and a heads is very small, but it's always there, and that little difference is what accumulates to give Bob an advantage at 0. We can always see that Bob is advantaged because this is always less than 0 here at 0. And as you go, you see more of this, it sort of flattens out, and again, it's getting very close together, so Bob's advantage is getting smaller and smaller, which we saw already, right? Bob's advantage was shrinking over time, but is always there. So you can turn this into a nice proof, and I have in the description, there's a nice written proof, if you're into that kind of thing, of why this means that Bob is always winning. All right, so that is it for how the value functions work and how they were used to calculate these probabilities of Alice and Bob winning, and why Bob always has an advantage, both from an intuitive point of view with this dog running on the field and how that translates into the proof that for any time t, Bob is always at an advantage. The thing that I didn't get to is proving these two formulas, 1 over square root of pi t and 1 over 2 square root of pi t. And because this video is getting a bit long, I'll put those in a second video some other time. So make sure you subscribe if you want to check that video out when it comes out. And in the meantime, I have this video for you, which is also about another classical problem with heads versus heads tails, if you haven't seen it yet.